Hey everybody, and welcome to our next video in this unit about gas laws, which is all about Avogadro's law. So yes, we're going to talk about Avogadro again. And in case you don't aware, which hopefully you are, because if you've gotten this far, you should know Avogadro's number. But Avogadro says that 1 mole of anything contains 6.02 times 10 to the 23rd particles of that particular element, compound, molecule, whatever. Avogadro didn't do just that though. So he did come up mostly with this right here. And it has to do more so with the gases and the volume that 1 mole of a gas takes up. So Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. So if I have two totally different gases that are at the same temperature and pressure conditions, those gases contain the same number of particles. Doesn't matter what gas they are, it doesn't matter what the molar mass is, but they take up the same volume. So for example, here is the image that's also in your notes. So let's say I have these 3 balloons, right? And each of these balloons contains 1 mole of 3 different gases. So this first balloon contains 1 mole of helium gas. This second balloon contains 1 mole of ammonia gas, and this third balloon contains 1 mole of oxygen. And if you count, these should all contain the same exact number of particles. Now, granted, there's not 1 mole in there because you'd be here literally all of your life drawing dots for these images. So, but they all contain the same number of particles. And because these are all 1 mole, but they're all comprised up of different elements, the molar mass of these is different. So if I have 1 mole of helium, that would have a mass of 4 grams. 1 mole of ammonia has a mass of 17.04 grams, and 1 mole of oxygen is 32. That's nothing new. That's a Chem 1 thing. We reviewed it at the beginning of Chem 2. However, at these conditions, if I have this at 273 Kelvin, if all of these are at the same pressure or at the same temperature and pressure, I'm actually missing pressure here. So I'm going to go ahead and take this little pen here and let's go ahead and write that these are also all at 1 atmosphere. So let's say 1 atmosphere for each of these. Let's write it. And 1 ATM and 1 ATM, because we definitely want to make sure that these are all at the same pressure. So I would just copy that down too. So at 273 Kelvin and 1 atmosphere, all of these gases, no matter what gas they are, take up the same volume. And for 1 mole of a gas at STP, which is what every one of these things are, the volume of that gas is 22.4 liters. Does not matter what the gas is. If I have 1 mole of any gas at 273 Kelvin and 1 atmosphere, that gas will have a volume of 22.4 liters. That's what Avogadro's law says. Not necessarily the 22.4 liters, but that if I have 2 gases at the same temperature and pressure, and there's the same number of particles, they will have the same exact volume. Okay, Avogadro's law. However, we can also relate this to the standard conditions, which is what this is showing down here towards the bottom. So at STP, at 273 Kelvin and 1 atmosphere, which is what each of these balloons are showing, a gas occupies a volume of 22.4 liters. If you had Dr. Clark, I believe you talk about 22.4 liters when you're doing mole conversions. I normally don't. I like to save it for this, but you might have heard that number at this point already. And we call that the standard molar volume of a gas. So this says that the volume occupied by 1 mole of a gas, of an ideal gas, at STP is 22.4 liters. So at STP, let's just take some notes here. So at STP, 1 mole of a gas equals 22.4 liters. 22.4 liters. So keep that in mind as we start doing stoichiometry problems with these gases. This image down here kind of relates back to Avogadro's law as well. So let's go ahead and take a look at this. So let's say I'm going through some reaction here, and in this case I have hydrogen gas, so H2, reacting with chlorine gas, and that's yielding 2 hydrochloric acid molecules. Now all of these are gases, so we want to include this little subscript of G on the end here. If we look at the coefficients of this, so 1 molecule of hydrogen gas reacts with 1 molecule of chlorine gas to yield 2 molecules of hydrochloric acid. We don't normally work in molecules though, we work in moles. And because every single one of these reactants and products are gases, because these are at the same temperature and pressure, we can also consider the volume that these gases occupy. So that's what this image is showing. Not only is this one molecule, but this is one volume. So one particular volume of hydrogen gas, whatever that might be, so one volume, reacts with one volume of chlorine gas, again, because both of those coefficients are 1, produces 2 volumes of hydrochloric acid. So look, I have this particular section right here. So this is 1 volume. But then I have 2 volumes because I have that second one attached to that. And that's because the pressure is constant. So here within this volume, we have to have the same pressure throughout because pressure is not changing. Because the pressure isn't changing, the amount of space that those gas takes up is going to be greater because I'm producing 2 moles of a gas from 1 mole each. I think this is easier to think about when you're actually doing problems, which is what we're going to do in the following sections. But this all comes down to those balanced chemical equations. So 1 volume of hydrogen gas, let's actually call this as a volume. Let's say I have, I don't know, let's call this just 2 liters. Let's say I have 2 liters of hydrogen gas reacting with 2 liters of chlorine gas. Question might say, how many liters of hydrochloric acid is produced? Well, if this is a 1 volume, let's say, and I produce double the volumes because my coefficient is 2, you should produce 4 liters of this gas right here. So you don't always have to do stoichiometry to figure these out. You can just kind of think about those balanced chemical equations and go from that. So this down here is more so Avogadro's law. I'm not sure why it's on this particular slide, but that's okay. Let's see here. It's kind of hard with this pad that I have here. This is down here is more so Avogadro's law. And on the next sample problem, we're going to go ahead and work with each of these. So this is more Avogadro's law. This right here is also crucial in AP chemistry because there's a lot of problems that deals with volumes of gases like this. Anyway, let's stop talking about it and let's just do some sample problems with the standard molar volume of a gas and also Avogadro's law. All right, so we are going to work strictly with Avogadro's law first, and we're going to be working with volumes of gases. So I think that this is really important just in general and especially in AP chemistry. You don't have to think super duper hard about a lot of these concepts, but if you just know that 1 mole of a gas at STP takes up 22.4 liters of space, or that gases at the same temperature and pressure have equal volumes depending on however many moles there are, you can easily solve these problems. So sample problem 9, A through D, we actually don't have to do a lot of math for it. It's just mental math, and there's not even any conversions with this. So let's just consider this picture here. So I found this online, and I thought this was a really nice representation of Avogadro's law. So We have nitrogen gas reacting with hydrogen gas to produce ammonia. And 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. But because at the same temperature and pressure, so these are at the same temperature and pressure, we're assuming they're the same, just because why would they change in a reaction unless you're altering them, but that's something totally different. So because all of these are at the same temperature and pressure, we can relate their volumes to the number of moles. So since 1 mole of this reacts with 3 moles of this to produce 2 moles of this, their volumes are also going to be to that general proportion as well. 1 volume of nitrogen reacts with 3 volumes of hydrogen to produce 2 volumes of ammonia. So using that, let's go ahead and solve these problems. So it's asking, I'm going to color code this for different problems. So we're going to use black for this one here. How many liters of hydrogen would be needed to fully react with 2 liters of nitrogen? Well, if this is 1 volume, right, 2 liters, we have to have 3 times that, 3 times the number of hydrogen to react with all of that nitrogen in terms of volumes. So your answer, 2 times 3, gives you an answer of 6. 6 liters is needed to react with that. And again, it's just a simple mole ratio step. So if this is 1, right, and there's 1 mole of this and 3 moles of that, 2 times 3 gives me 6 liters. Let's try B. And again, these are easy because those pressure and temperature conditions aren't changing. Let's go ahead and solve this one in pink. How many milliliters of ammonia, so how many milliliters of ammonia would be formed if 15 milliliters of nitrogen reacts completely? Again, look at those coefficients in the top. If this right here, if 1 mole or 1 volume of nitrogen produces 2 volumes of ammonia, the answer must be 30, right? It has to be double that. So your answer is 30 milliliters. You can do stoichiometry to solve these problems, but why would you do that if you can just look at the coefficients? It's much easier to do it this way. So I just erased all that work up there, and I'm just going to pick a different color again to show you C. So let's do green, I suppose. How many meters cubed? This is a unit of volume as well. Don't let the units get you worked up because it's still a measure of volume. You're probably familiar with centimeters cubed. 1 centimeter cubed is actually the same thing as a milliliter. So a meters cubed is also a unit of volume as well because you have length times width. So length times width times height. That was totally not what it was, but you get the idea. Length times width times height, you're able to figure that out. That was a terrible, terrible drawing, but I think I got it maybe. Okay, there you go. So how many meters cubed of hydrogen? So how many meters cubed to produce 30 meters cubed? This one's not as inherently obvious to me, at least, because we're not working with a 1 ratio here, but we can in fact still do this mentally. So let's go ahead and think about it. So I have 2 moles of ammonia, or 2 volumes, let's say, and 2 volumes is equal to 30 meters cubed. So I'm just going to go ahead and half that to find out what's 1 volume. So if I do that, 1 volume of this gas, or in this particular equation, would be 15 meters cubed. So if 1 volume is 15 meters cubed, and for hydrogen gas, I have 3 volumes, well, 15 times 3 gives me 45. 45 meters cubed would be your answer for that one. So again, you don't have to do more work than you think. A lot of these problems aren't necessarily going to be super duper hard, but you just have to sit back and think. So, all right, well, if this is 2 moles or if this is 2 volumes, let's say, I know 1 volume would only be 15 meters cubed. And if I have 3 volumes of hydrogen, 3 times 15 is 45. So let's try D. D's in blue. So how many volumes? Notice here, there's not even a unit. We're just going to work in units of volumes in this case. Of both nitrogen and hydrogen are needed to produce 12 volumes of ammonia. Again, try to simplify this as best as you can. Write it out. Sometimes writing out something like this with a balanced equation makes all the difference. So, all right, so there's 2 volumes of ammonia right up here. So 12 divided by 2 means that every one is 6 volumes. So every one, we'll say every 1 mole in this problem equates to 6 volumes. So let's go ahead and use that balanced equation to go ahead and figure this out. The number of nitrogen that's needed would be just 1 volume because its coefficient is 1. So I'll say nitrogen is just 6 volumes. And then hydrogen has 3 times that. So 6 times 3 would be 18. It's hard to explain what the word volumes means, to me at least. So just think of it as another unit, right? Another unit. If I had some area of space, some amount of a gas, and that gas was equal to 6 volumes, but I need 3 times that amount of gas in order to react with that. Well, that would be 18 because 6 times 3 gives me 18. So it's a little hard to explain, but again, it's the same exact thing as if it was like with units. It's just a volume measurement. I like to go over that because, like I said, this is also important in AP chemistry. And I don't think it's that hard to understand. So I think it's really nice to just put in here and to reference every now and then just to keep your mind sharp on that. Using actually the standard molar volume of a gas. So this was more work with Avogadro's law right here, sample problem 9. Let's go ahead and work with that standard molar volume of a gas at this case. So that standard molar volume of a gas says that 1 mole of any gas at STP occupies a volume of 22.4 liters. So because we know this piece of information, we can use 22.4 liters very readily in problems like this. So what is the volume of 7.08 moles of nitrogen gas at STP? That's important. Because we're at STP, we can use that 22.4. So I have 7.08 moles of nitrogen. And we have moles of nitrogen, 2 liters of nitrogen. Because we're at STP, 1 mole of any gas at STP occupies a volume of 22.4 liters. So this is just a very simple one-step problem. So to solve for this, you would just multiply straight across, and your answer is 159 liters of nitrogen. You try sample problem B right here. Try sample problem B. So you're working backwards from what we just did. Answer for B is 0.630 moles of hydrogen. So you did just have to flip that conversion factor in order to solve this problem, of course, because your units have to cancel out. Let's go ahead and try C together. So a chemical reaction produced 98 milliliters of sulfur dioxide at STP. What was the mass of the gas produced? So I'm going from the volume in milliliters to the mass of the gas. So, of course, what relates everything to everything else in chemistry is the number of moles. So let's go ahead and convert that 98 milliliters to moles. And I can use 22.4 for that because it's at STP. You might be wondering, well, what happens if it's not at STP? Oh, don't you worry. We're going to talk about that later. Not in this video, in a different video. So let's convert milliliters to liters first. Now it's up to you. You can just do this before and then plug it in. Sometimes I like to just write it in there. Ultimately, it doesn't matter. So let's convert liters of SO2 to moles. And I know that 22.4 liters, I didn't put the SO2 there for this one. You don't have to, is equal to 1 mole. And now that we're in moles, you can in fact convert this to the number of grams because you can do that in just one step. Moles of SO2 to grams of SO2. So sulfur dioxide is SO2. That's why it's so important to remember how to write formulas given the name. And just to make your life a little bit easier, I will give you the molar mass. It is 64.07. And if you solve for this appropriately, you should get an answer of 0.281 grams of SO2. And that's it. So in this video, we covered Avogadro's law, which is using those volume relationships depending on the coefficients of a balanced chemical equation. And we also have the standard molar volume of a gas. So 1 mole of any gas at STP occupies a volume of 22.4 liters, which allows us to do these conversions in sample problem 10. As always, if you have any questions, make any notes, put a star by something, highlight it, make sure you ask me. Don't keep to yourself. They're not going to learn anything that way if you don't ask me any questions. Otherwise, I will see you in the next video, which is all about the ideal gas law. I hope you have a wonderful day, and I will see you soon. Bye.